In this video, we're going to talk about what gradient descent is. So if you're using machine learning models, if you're working in statistics, and you want to know at a very basic intuitive level what gradient descent is, then this video is for you. Now, when I was learning about what gradient descent is, I was like, why do I have to learn about it? What's the use of it? The name sounds horrible. Like gradient descent, you're descending into something. Like it was not very visual for me, because how can it be? Let me show you an example. This is what the graph for your gradient descent looks like, and this is the top view of the same graph. It's not very intuitive, it's just there. So then what I did, I tried to understand at a very basic level what it does. So if you're not able to visualize it, at least understanding the mechanisms that what the thing does is really helpful. Because what I believe is statistics in general is not very a visual concept, right? So try to understand the mechanisms behind it is the way to go. And once we do that, we'll be good. Before moving forward, I'm going to assume something. I'm assuming that you generally have a basic understanding of what linear regression is, right? It's really easy. We got like independent variables, we got dependent variables. We're trying to use independent variables to predict the dependent variables. A simple example is to predict house prices. Looking at this chart, on y-axis we got predicted log prices, and on the x-axis we got actual log prices, and the red line which you see is our best fit line. So this is a simple linear regression example. So that was the simple regression chart. Now I'm assuming one more thing. I'm assuming that you know what a loss function is. If you don't, it's really easy. I'm considering an example of MSE. It's a loss function which we use for linear regression. So MSE is mean square error. What we want is, we got yi over here. That yi is the original house price. This is the house cost right now. Yi hat is the value which my model predicted. And that difference is what the error is. For example, the real price of the house is 700,000. My model, it predicted the price to be around 300,000. Subtract that, forget about the square, but just subtract that, around $400,000 is my error. And what we do is, we need to minimize that error as much as possible. So 300,000, it's not really good, right? If your house is going for $700,000, I'm predicting 300, a big loss, right? So I need to minimize that difference as much as possible. You can use MSE to do that. Now most of you will be, okay, I know the linear regression, I know what the loss function is. What about the gradient descent? Well, here's the thing. MSE, what does MSE tell you? The difference between what you predicted versus the actual value. It does not tell anything about how you can improve the model. Nothing. A house costed 700,000 in reality. My model predicted 300,000, 400,000 was the error. What am I going to do with it? Okay, it does not tell me anything, right? So knowing MSE alone is not going to help you improve your model in any way, right? That's just not going to help you. So I'll put it this way. It's like being told how wrong you are without being given any clue about how to fix a problem. That's a nice quote which I found online. So this is where gradient descent comes to play. While MSE tells us how bad our model is doing, gradient descent shows us how to adjust the parameters, like the slope and the intercept of the linear regression, to minimize that MSE. Essentially, gradient descent is the process we use after calculating the MSE to figure out which direction to move in to reduce the error. So should I reduce my slope? Should I increase my slope? What should I do with the intercept, right? To get that best fit line. How do I get this best fit line? What should I do? That's what we are trying to find out using gradient descent. Okay, let's keep to our example of predicting house pricing in this particular case. We are using some sort of loss function. In gradient descent, we usually call it a cost function. So we are using a cost function. In our case, we are using MSE. What does MSE tell you? That how far off your predictions are. Okay, good. We know that. What gradient descent is going to do is going to help adjust the slope and intercept of our line. So you see that line? For that line, it's going to help us to adjust the slope and the intercept to gradually reduce the error. First, we'll have a huge error. It'll go down, down, down until we reach the optimal value. So like with each step, the line shifts slightly, fitting the data a bit better. So eventually it reaches the best possible fit. And that's it. That's all gradient descent does. You don't have to look at the chart or some fancy rainbow color thingy like sheets. You don't have to do anything. Gradient descent at its very base, it's just helping you to find the best fit line. That's it. Boom, bam, you're done. That is what gradient descent is. Now I'm going to show you an Python example. I have a code. We'll see the code in a bit to get like a bit more technical. But before that, let's just understand the steps which you're going to take in like our example of the predicting house price, right? First thing, we initialize the parameters, the slope and intercept randomly. You see that line at the very bottom? It's going to go up, right? Initialize it randomly. Slope, intercept, you get some sort of line. We compute the cost function. What is the cost function in our case? MSE, right? Which tells us how bad our current line is. If your line is like really low in this particular graph, your model is real bad, right? And your model is performing very terribly. Now we do what? We have the MSE, that's just the cost function. We compute the gradient, which shows us the direction we need to move the line to reduce the error. If our line is way up above over there, we got a huge error. If the line is way below the optimal values, we got a huge error too. Now, depending where our line is, we take small steps in that direction, guided by a learning rate. Learning rate is something we'll see in the actual Python example. So it is a parameter that controls how big or small steps to take, right? If your line is at the very bottom, if you take a big step, you're missing the optimal parameters. If you take a small step, then you're gradually gonna reach your best fit line, right? So that's the way to go. That's learning rate. We'll look at it with an example. Now what we do is we repeat this process until the cost function is minimized and we have found the best fit line. And we can actually observe this. If you're using training and testing, we can actually observe that the MSE keeps on going down. Before we move on, understand that there are main three types of gradient descent. First is the batch gradient descent. Now, this is the most common type of gradient descent, and it uses the entire training dataset to calculate the cost function's gradient. Entire dataset, batch gradient descent. Second is stochastic gradient descent. So what this type of gradient descent does is it updates parameters for each training examples individually. Take individual examples and then update the parameters. So that's the second. First one is the batch, second is stochastic. Third one, and this is what we have used in this example, is the mini batch gradient descent. This variance divides the training data into batches, right? Which are then processed sequentially. So you have batch of like 30 observations. And this particular thing is used commonly in deep learning models. So mini batch gradient descent is something what we are using in this particular example. Okay, so now this is not a Python class. You might be very familiar with the Colab, with Jupyter Notebook, and whatever, Anaconda, whatever you're using. So I'm just gonna zoom past this code, right? I connected my Google Drives. I got all the imports. I got some, this is the important one for our model, MSE, then train trace split. So I'm gonna split my training testing data and I've standardized my data too, right? So we are gonna have some of them imports. Here, I got the same example. We got some house features or house attributes. So we got total basement square feet. Does the house has central AC or not? Living area and the sell price, right? This is what we want to predict. So this is our predicting variable. Everything else is our independent variable. Now, this is basic pre-processing. What I did was, you see this central error, it's y. So it has central error, y. It doesn't have central error. No, we don't want this, right? There's no use. We need to convert central error into direct numeric. So if you have, then 1. If you don't have, then 0. That's the pre-processing. So we got 1 for all the y's. That's it. I'm checking if we got any nulls in our data. We have a row where total basement is null, so we just got a row. We will just take that. We'll just take that row out. We'll check it again. We have no nulls. Separate predictors and target variable. I'm going to keep my sell price in y because that is what I'm predicting. And I'm going to keep everything else. So I'm just going to drop sell price and everything else I'll be storing in x. So those are my independent variables. I'm going to use x to predict my y. We got around 3k rows, 5 columns in my x and only 1 column in my y. That is my predicted, or that is what we are predicting. We do a simple train test split. We did a 70-30 split over here. Random state is 18, shuffle true. You can shuffle the values. We also need to standardize our data. So I'm transforming my train and I'm only transforming my test. So if you don't know what standardization is, it's really important. You always need to standardize your data. I might give something in the description. Go and check why you need to standardize your data in this particular scenario. Coming to the important part, this is our linear regression model, which I've built from scratch. Okay, it's really easy to do linear regression in Python. You just import a library. Let me show you down here. This is it. That's the code you need for linear regression in Python. Model is equal to linear regression. We got this linear regression from sklearn model. But to use gradient descent, which we have over here, I've wrote this linear regression model from scratch. So just follow along. First thing first, initialize parameters. Now this you don't need to really worry about because here I'm also taking care of bias because there will be bias in our data. That's why I'm initializing that as 0. I'm adding 1 more column. Don't worry about it right now. Prediction. This is simple dot product. This will give you the prediction of your features, whatever the features you have features in X. W is the same thing, it's bias. Don't worry about W, but worry about X. These are the features. You multiply that with weights and you get some sort of prediction. In our case, what the prediction will be? 300,000. That's my prediction. Compute cost. As I said, we are going to use MSE in this particular example. So this is simple MSE, the same formula we saw on the slide. 1 upon n summation y minus yi at bracket square. Simple cost function. That's how we're going to calculate MSE. So we got our predicted value 300,000. We got our compute cost. What's the difference over here? 400,000. I need some mechanism to get my MSE down. You need to minimize the MSE. That's why we are using gradient descent. Update weights is my gradient descent. Here is where I'm doing all the gradient descent things. Let's see. We start with a random choice. We start with a batch size. Where are we getting the batch size from? Let's see. Update weights in our train linear regression model. Let's skip this part for now. We'll come back to it later. Define train LR. This is where I'm doing my linear regression from scratch. X train, Y train, X test, Y test. Learning rate is 0.001. So this is the learning rate with which my gradient descent is gonna take steps. So 0.001, very small steps, right? Iteration 1300. You can adjust it. I'll show you why I kept 1300. Batch size is 32. We are doing mini gradient descent, right? Mini batch gradient descent. Then feed intercept is equal to true. Check this out. These two lines, don't really worry about it. It's again for the weights. We're calculating weights over here, which will go in W. In features, number of features. So X train has what? Our features. So all the 5 features we had in our training data set are going to go into features. W is the weights that take care of bias. I'm creating 2 lists to just store the training losses and testing losses. In this function, I'm just iterating. I'm just going to do iteratively. Like the steps you see over here, iterations, I'm going to iterate that many times to check, are my training and testing losses going down? Okay. So here, I'm just going to iteratively do the compute cost to get the train lost, do the same compute cost to get the train lost, and I'm going to stop after these many iterations. I'm just going to return them. That's it. So this thing does the gradient descent iteration. This is for updating weights, taking care of bias. You don't have to worry about that for now. You can use it. You don't use it. It's up to you. But most of the models, if you're doing linear regression, you should check for the bias. It's like how much weight should each feature get. For example, basement, the square footage of basement should get like a less weightage than if a house has AC or not, right? You need to adjust those weights too. So that's really important. Prediction, compute cost is our MSE. So 3 important functions. This thing calculates our gradient descent. This plots our gradient descent. You can see for iteration 0, train loss is this, test loss is this. Focusing on the training loss, you can see it's going down. 38,000, 31, 25, 20, going down. 46. So it like went way down. Train loss, it went way down. So you can see MSE loss versus gradient descent iterations. It went way down. Now I reached an endpoint over here, because now here instead of 1300 iterations, if we do, let's do 1700. Let's run this. You can see after like this point, it keeps on going down, but it flattens out. So this is not a huge difference than this thing. So it like kind of flattens out. We can do more iterations. Let's do 2500. Let's see what this gets us. Now this is not really useful. We can see, oh, steep going down in losses. This is really good. This just flattens out. You can see over here 15, 15, 16, it is still going down. We can still go for it, but it flattens out, and this is just going to go straight. So that's where we need to block our iterations. So yeah, that's it. This is like a real life example. I've just selected like 1300 as my final iterations, where the MSE was the lowest for training as well as testing. So this is a simple example. I'm going to post this IPYNB, the Python file, in the description. You can check it out. If you want to learn more about the weights, what I'll suggest is just copy this code, put it in ChatGPT. Let's do that. Put it in ChatGPT. Tell ChatGPT, you know what? Explain what the weights are over here. It'll tell the same thing which I just told you. You're using weights to give for like each feature how much importance you should give. Something will have less importance, something will have more importance, and that will affect your MSE, right? So just put this code in there, and yeah, that's it. That's what gradient descent is. You're trying to find best fit line where you minimize the loss, where you have the least MSE. This figure might make more sense now. Consider this as you're on top of the mountain. If you're at the peak, you want to go down, you want to minimize the losses, you're going to take big steps. Okay? You're going to get big steps at the beginning. Once you reach like a bottom, you'll start to slow down a bit, right? Because you don't want to overdo and go somewhere else. You need to go to valley. You don't want to go down and start climbing up again. You don't need to do that, right? That's what's happening in MSE or in gradient descent. We are minimizing the MSE, and once we reach our optimal values, that's where you're going to find your best fit line. So don't really worry about this graph. They are not very intuitive, because first thing, it's multicolor and it's in 3D. So I don't really get it. But yeah, I hope that this video was useful because I was like, oh, you know what? I'm learning about this thing. Let me just post it. So thank you for watching, and I'll see you in the next one.